Hello everyone, I'm Hayan Kim from the Intelligent Computational Imaging Lab. Today I'm going to present our work, RoMaP, Robot 3D-Masked Part Level Editing in 3D Gaussian Splatting with Regularized core distillation sampling. So before start our presentation, what exactly is RoMaP? RoMaP is our proposed method for 3D part segmentation and editing. For 3D part segmentation, our method achieves strong part level results even under open vocabulary settings. For 3D part editing, RoMaP enables highly controllable edit. For example, we can change her hair into coral, or we can separately edit objects like bulb and lampshaded, showing strong part level controllability. Before we go in deeper, I have some questions. We emphasize part level in this paper, but why does handling part is important? In robotics, interaction requires part awareness. It means that we need to know which part is relevant for grasping to enable better affordance-based tasks. And in 3D editing, part level control enhances asset customization. If we want to change only a small part of the complex scene, then regenerating the whole scene is computationally inefficient. Such as if we want to change her hair into red, or if you want to recoloring a couch into purple, we doesn't have to regenerate the whole things again, just edit some part of it. This is why 3D part editing is crucial. But many existing editing methods already perform well in the instance level. But when it comes to a part level editing like changing the eye color into old eye or editing with drastic prompts such as giving someone an emerald nose, our method achieves significantly better results. Now let's look into our method. Previously, I explained why we need 3D part segmentation and editing method. For that goal, RoMaP proposed this pipeline. It may look a bit complex, but I'll walk you through in step by step. Before going into each component, let's start by analyzing the challenges in both segmentation and editing. The first one is the lack of accurate part level models, so only noisy estimations are available. And the second problem is that in most methods, each Gaussian contains only a single segmentation label, which make it difficult to capture noisy 3D information. In 3D editing, there are also two major challenges. The first one is that it's hard to preserve unchanged area during generation, and the second one is that including larger changes in only a small region is very difficult. Now let's go back to the first task. I'm going to discuss each problem one by one. For the problem of lacking part-aware model, we use an attention information of Stable Diffusion 3 as a cue for part-aware segmentation. But as you see in this GIF, the attention map is too noisy to use directly. This means there is an inconsistency when apply segmentation label to the same Gaussian. But actually, 3D graphics has already faced the similar challenges before. For example, in this picture, there is a color variation caused by lighting conditions. So we need different color even within the same region. Then how did they solve this problem? They use spherical harmonics coefficients to represent the color of Gaussian. So the RGB color of single Gaussian varies depending on the view direction and is calculated with SH coefficient. This allows different colors to be assigned in different view direction. Inspired by this, we add the Gaussian segmentation label as an SH coefficient. This means we can assign different labels from the same Gaussian depending on the view. In this picture, we can assign a whole different segmentation label, such as hair at the view direction 1 and the face at the view direction 2, and we call this the mixed label property. After assigning segmentation label from each view direction, then we calculate its softness. If the label varies significantly across viewpoint, the softness of the SH coefficient becomes higher. As shown in this picture, Gaussians with higher softness value are mostly located along the edge side, where uncertainty is high and the information tends to be fluctuated. Using this value, we select low softness Gaussian, which have high confidence information, as an anchor to apply on neighboring laws. so that finally we could get robust value on part level 3D segmentation. Now let's move on to the 3D part editing case. Here we also have these two problems. To resolve them, we introduce regularized cold distillation sampling, which enhances the controllability of SDS loss by leveraging two different regularizers. The first regularizer 1 is a Gaussian prior remover and masking. This prevents changes in unwanted areas. SDS loss is strongly biased toward existing visual priors, so Gaussian prior remover eliminates dominant colors, and this helps to induce larger changes in target area while preserving the other region. And for explicit 3D masking, the SDS loss normally acts in all directions, driving global variations. But by using 3D masking, we explicitly block gradient updates in unwanted region. And in contrary, for inducing larger changes in only a small region, we use Regularizer 2, anchored L1 with SLAM editing image. SDS loss is weak at handling subtle changes, so it requires an anchored image as reference. But as you see in this picture, when using a prompt change her nose into croissant, some image editing methods such as instruct pix-to-pix and plug and play either completely fail or, like SD3 in painting, produces almost no visible changes. This indicates that even in image editing problem, inducing larger changes only in intended part is still difficult. To ensure strong local changes while preserving global identity, latent features must be carefully mixed during generation. So by using a schedule factor aligned with time step, SLAM improves the controllability of the images. Looking more closely to this pipeline, the SLAM method mixes two different types of latent, the original image latent ZT ORIG and the simultaneously generating latent ZT aligned with the given prompt. The latent ZT contains rapidly changing information that reflects the prompt, while ZT ORIG consistently preserves the original image information. By combining these two different sources of latent information across time step, the method achieves the following formulation in the below of the pipeline. And here, the factor FT plays a crucial role. If FT is mixed in too strongly at the early stage, too many parts of the image change. And if it's introduced too late, almost no change occurs. As you see in these pictures, when trying to turn the nose into croissant, mixing too early stage causes the entire face to turn into a croissant, while mixing too late result is no change to the nose at all. To better guide this transformation, we measure CLIP and SSIM scores across time step. The CLIP score reflects how well the change aligns with the target prompt, while the SSIM score indicates how well the unchanged areas are preserved. From this analysis, we observe that the both scores peak when mixing occurs around the middle time step, which allow us to effectively induce the diverse and controllable change in the image. Finally, let's look at the experiment. Here's our 3D part segmentation result. And we compare our method with previously open vocabulary 3D segmentation method, such as Langsplat and Le Gaussian. As shown in this table, our method shows strong performance across all benchmarks in 3D part level segmentation. And for 3D part editing result, we also demonstrate high quality outputs such as a man with butterfly leaves and a man with gold bell nose. And for more quality results in our controllability in editing, we change our Superman's face into a Joker or even a Batman. And moreover, in complex scene, we achieve high quality in both segmentation and editing tasks. As you see in this picture, we can change a color of a mug into pink, or we can change the pirate hat into a white one. And we compare our method with nerve-based baseline and Gaussian splatting-based baseline, and also with generative method. And as you see in this table, our method shows the best performance among all. So this brings us to the end of my presentation. Thank you very much for listening.